Hi Calc AB. This is a video about related rates. So we're going to start with a basic example, y equals x squared. For a lot of the year, we would ask you to take the derivative of y with respect to x. And so we would operate both sides like this. And we would end up getting dy dx is equal to 2x. But when you take the derivative of y with respect to t being time, things are a little bit different because both of the variables can be changing with respect to time. So this side here becomes dy dt, and the right side becomes 2x times dx dt. You take the derivative of each of them as you would, but then you have to multiply by how each of the variables are changing with respect to time. So this has a dy dt and this also has a dx dt. You can think of it as chain rule. So I'm going to go to a review guide that we had back in our related rates unit, and I've put this in your binder also, and I'm going to go through a few examples. So here's the function p equals 3 pi m squared sine of theta, and if you notice there's three variables here, and each of these questions is asking you to do dp dt, so find the derivative of p with respect to time under different conditions. So if m is held constant, all of this right here is just a constant. So when you take the derivative of both sides with respect to time, the constant stays as it would stay in any other problem. The sine of theta's derivative is cosine theta, but then you have to multiply by d theta dt. It's that chain rule idea. It's how theta is changing with respect to time. In part B, m and theta are both functions, and so this is no longer just a constant. 3 pi is a constant, and that can be factored out. Or you could treat this as this function, the first function, times the second function. It doesn't matter how you approach it because you'll get the same answer. So because you have two different functions here, you're going to have to use product rule. So 3 pi m squared is the first function times the derivative of the second plus the second function times the derivative of the first. And again, in this one, you're going to need to have a dm dt by chain rule. So anytime you're dealing with related rates, you're going to have to multiply by how each of the variables is changing. There's a lot of good problems in here. The ones I'm going to fast forward to are those that give you the equation. So I'm going to look at number 17. A particle moves along the curve y equals root 3 plus x to the 5. As it reaches the point 1, 2, the y-coordinate is increasing at a rate of 3 centimeters per second. How fast is the x-coordinate of the point changing at that instant? And indicate units of measure. So we're going to take the derivative of y with respect to time. There's a whole bunch of chain rule happening here. Multiply by the derivative of the inside, multiply by how the x value is changing with respect to time. As it reaches the point 1, 2, the y-coordinate is increasing at a rate of 3 centimeters per second. So this is the exact same thing as dy dt, and it's positive because it says that the y-coordinate is increasing. So 3 equals 1/2 times 3 plus 1 to the 5 to the negative 1/2 times 5 times 1 to the 4 times dx dt. The nice thing about any related rates problem is they will give you enough information except for the one thing that they ask you to find, and so you're just going to have to plug in a bunch of numbers. All right, so here we go. 3 is 1/2 times 4 to the negative 1/2 times 5 dx dt. Take a second and solve that equation for dx dt. So I get 4 over 15. The last thing that they want us to do is indicate units of measure. So that's asking us what are the units for how the x-coordinate is changing. So the units for the y-coordinate changing is centimeters per second, and we don't have any other units for the x. So this will be centimeters per second. The other way that you can come up with it is look at the different units for the numerator and the denominator. The denominator's got to be time, so you have to have some unit of time in there, and then your x value is a distance because you're dealing with an x-coordinate. So your full answer is 4/15 centimeters per second. One last thing about the problem, a clue that you're going to have to use a related rate is this phrase right here, or a variation of that phrase. How fast is the x-coordinate of the point changing at that instant? So at that instant indicates a particular moment in time, and they're also talking about how fast, so how the variable is changing. Let's go back to number 16. A cylindrical rubber cord is stretched at a constant rate of 3 centimeters per second, assuming the radius is the same along the entire length and its volume does not change. How fast is its radius shrinking when its length is 50 centimeters and its radius is 2 centimeters? Indicate your units in your answer. So here again is a situation that they give you the formula, and you know that the formula you get to use is perfect because it's the formula for the volume of a cylinder, and they're telling you that you have a cylindrical rubber cord. So I'm going to use product rule to come up with my derivative because both the radius and the height of this cord is changing, so you need to use product rule. So this is my first function, and this is my second function. So we have pi r squared as my first function times the derivative of the second, plus the second times the derivative of the first. And because both variables are changing, you need to multiply by dh dt. So now we're at the point where we get to plug in. And this did not indicate the instant part, but it says how fast is its radius shrinking when its length is 50 centimeters and its radius is 2 centimeters. That is a moment in time, a specific instance. So even if the word instant isn't there, it does indicate that we need to use a related rate. So take a second and plug in what you know, pause the video, plug in what you know, and see if you get what I get. All right, these are the values that I substituted. The text says that the volume does not change, so that means it's 0. The dV/dt is 0. And it told us the radius was 2, the length is 50, so that's the same thing as the height. And here again, we're left with the only thing, and that's what we're trying to find. So now we just solve for dr dt. So I subtract this amount over to the other side, so negative 12 pi, and then I can divide by 50 times 2 pi times 2, and negative 12 divided by 4 is negative 3. So we end up with negative 3 over 50, and the units will be centimeters per second. So that's a recap of related rates. I would go back and try as many of these problems as you can. This is also a document with linearization if you'd like some extra practice on that.